Welcome to Lecture 2.1, the fundamental theorem of linear differential equations. We'll start with some definitions that you should have already seen in your Intro Differential Equations course. To begin, a first-order differential equation is of the following form. So y prime is some function of t and y itself. Now you could define first-order ODE more generally, just any expression involving y prime and t and y. Maybe you can't isolate y prime and solve for it, but realistically, those things, as far as I know, don't really come up in modeling or in practice. So for all intents and purposes, you might as well just assume that these are all the first-order differential equations that we're ever going to see. Similarly, a second-order differential equation is of the following form. Y double prime equals some function or expression involving t, y, and y prime. So you know this, of course. Here's something that you may have forgotten. This is what a linear and homogeneous ODE is. So we'll start with the first order case. A linear first order ODE can be written as follows. Y prime plus a of ty equals g of t. It is, moreover, homogeneous if g of t equals 0. Similarly, a second-order linear ODE can be written as y double prime plus some function a of t times y prime plus b of t times y equals g of t. And it is homogeneous if g of t equals 0. So several things to notice about this. First of all, for both of these, a of t and g of t, and in this case b of t, these don't need to be constants. They can be arbitrary functions, which may be surprising, because what this means, for example, is things like y prime plus e to the t squared sine of t, y equals t cosine of t, something like that. That is, in fact, a linear differential equation, even though it contains these terms, which are highly nonlinear in t. Here's an explanation for this terminology. Let's consider a linear ODE of the same form that we did above. Then this thing, d dt plus a of t, let's call that capital T, is a linear differential operator on the space C infinity, that is, of infinitely differentiable functions, or smooth functions. Explicitly, this means that t applied to some function y is computed by just writing out the operator and tacking on the function y and then multiplying through as if you would in a polynomial. So if you do that, the d dt attaches to the y, and you get dy dt, and then a of t attaches to the y, and you multiply those together. Explicitly, this is y prime plus a of t times y. So indeed, this guy is a differential operator. And so why is it linear? We checked something like this in an earlier lecture, but let's do it again for good measure. I'll go quickly because this is not the first time we're seeing this. So we have to show that t of some linear combination, let's say c1 y1 plus c2 y2, we have to show that that is equal to c times t of y1 plus, or c1 plus c2 times t of y2. So just by definition, this is d dt plus a of t times c1 y1 plus c2 y2. So now we can multiply this out just as if we would a polynomial. The operator attaches to the function. So if we do that, let's do the first two terms, and the first term here and the second term here. So we get c1 d y1 over dt plus a of t times, so it's a of t times c1y. Well, I'm just going to put a brackets here. So a of t times c1 times y1. And then the same thing in the second term, we get c2 times, here we have d dt times y2, so that's our dy2 dt, and then the last term we have a of t times y2, so plus a of t times y2. And indeed, this is c1 t of y1 plus c2 t of y2. So this is indeed linear. While we're on the topic of this linear differential operator t, notice that the kernel of the operator is the set of all solutions to the related homogeneous ODE. And by that I mean take the original ODE, which is up here, and set g of t equal to 0. So this is inhomogeneous, and if we set the right-hand side equal to 0, we get in a homogeneous ODE. So notice, what does it mean? So why is this true? Well, by definition, the kernel of t is the set of all functions y such that t of y equals 0. Now what does it mean if t of y is 0? So this is the set of all y such that this guy applied to y equals 0. So that's, in other words, this is equal to 0, such that y prime plus a of t y equals 0. So that's what the kernel of t is. It's a little bit different than the solutions to the original ODE. Which, by the way, what are the solutions to the original ODE? What's another way to write it? Well, it is the set of all y, functions y, such that ty doesn't equal 0 now, but equals g of t. So this is the set of solutions to the inhomogeneous ODE, and this is a set of solutions over here to the homogeneous ODE. Now, many of you know the punchline. Hopefully you remember it from your intro differential equations class, but if not, I'll write it down here. The general solution is any particular solution yp that solves this ODE plus the kernel of t. So plus the kernel of t. So if we take any particular solution and we add anything that vanishes by t, then we get another solution. And this is in fact the set of all solutions. So we'll formalize this even more soon. But first, I want to show you the same thing, but for second order ODEs. So consider a linear ODE at second order, so it's y double prime plus a of t y prime plus b of t y equals g of t. Then this guy, let's call it capital T again, and this time it's d squared dt squared plus a of t times d dt plus b of t. That is a linear differential operator, again on the space of smooth functions. It doesn't really matter if we consider real valued or complex valued. That's why I didn't specify it. In other words, t applied to a function y, it's this big creature put in front of y, so you multiply it out with the distributive law. And so this thing attaches to d squared over dt squared, and you get y double prime. This thing attaches to this, and you get a of t times y prime. And then these things multiply together. So here it is, t of y equals this guy. As before, the kernel of this operator, that's the set of all functions that get killed by t. So that is the set of all solutions to the related homogeneous ODE. Here you just take the original ODE and you set that last term g of t equal to 0. And once again, the general solution here is going to be any particular solution that you can find plus the kernel of this differential operator t. So often this is called the homogeneous solution. That preview that I just gave you is how to solve linear inhomogeneous ODEs. and we'll cover that in more detail in a few lectures. The topic of this lecture is how to solve homogeneous ODEs. So here's the fundamental theorem. Let's let T be a linear differential operator of order n. That means the highest derivative that appears is the nth derivative. And once again, we can just assume that it's an operator on the set of smooth functions. I don't really care if they're real valued or complex valued. Regardless, the kernel of T is an n-dimensional subspace. Now, here's what this all means. Well, first of all, let's just assume that our functions are complex valued. So I'm just omitting the c that goes right here. So in the first order case, the general solution to an arbitrary first order linear homogeneous ODE like this, well, it's the kernel of the corresponding linear differential operator, ddt plus aft. And by this fundamental theorem, that kernel is a one-dimensional subspace. So if it's one-dimensional, that means it has a basis consisting of a single element, aka a single function. So that means that the general solution is all scalars c1 of some function y1 of t. So in other words, find any function that solves this, and then just multiply that by a constant, and that is the set of all solutions. Formally, we say that y1 is a basis of the so-called solution space, because it's a vector space of solutions to this ODE. Let's go up to n equals 2. The general solution to an arbitrary second order ODE is just the kernel of the corresponding linear differential operator, d squared over dt squared plus a of t ddt plus b of t. By the fundamental theorem, that is a two-dimensional subspace, which means it has a basis consisting of exactly two elements. Remember that the dimension of a subspace is equal to the number of elements in its basis. This means that there are two functions, y1 and y2, such that every single solution is of the form c1 y1 plus c2 y2. Here we say that y1 and y2 form a basis of the solution space. Once again, the general solution to this homogeneous linear ODE is a vector space, and this is a basis. Now let's compare these two examples and see how much choice we have in y1 and y2. In this first case, the solution space is a one-dimensional vector space. So if this is a zero vector, or in this case zero function, then any non-zero y1 is going to be a basis for this one-dimensional space, because the set of all vectors on this line is just c1 times y1. So y1 it's not unique, but it's unique up to scalar multiples. Whereas in this case, y1 and y2 are far from unique. So here's sort of a cartoon of a two-dimensional vector space. So if we take any y1 and any y2 that are not scalar multiples of each other, then, well, those things span the two-dimensional space. So they form a basis. So here's an example of where y1 and y2, where you can choose vastly different things for y1 and y2, outside of just scalar multiples, which of course we're free to do. But let's consider the ODE y double prime equals negative y. So this is linear and homogeneous. Well, because if you move this to the left-hand side, then g of t, or the right-hand side g of t, is equal to 0. And hopefully you remember that the following are both solutions to this ODE. So y1 of t equals cosine of t, and y2 of t equals sine of t. Well, that means that the general solution is of the form c1 cosine of t plus c2 sine of t. So this is the two-dimensional subspace of all solutions to this ODE right here. But there are other solutions. It's not hard to check that y3, let's say y3, say of t, is e to the it, that is also a solution. Notice if you take the derivative twice, an I squared pulls out, and that's -1. And y4 of t is e to the minus it is also a solution. So another way to write this general solution is as c1 e to the it plus c2 e to the minus it. So to summarize, we say here that cosine of t and sine of t is a basis for the solution space, but here's another basis, e to the it and e to the minus it. That's also a basis. And in fact, any two solutions to this ODE that are non-scalar multiples of each other are a basis as well. So here's another basis, cosine of t e to the it. So we'll do more on this later, especially in the next lecture. Hopefully, at this point, it should be clear how this all extends to ODEs of order greater than 2. Let's summarize what we learned. Here's the big idea. To solve an nth order linear homogeneous ODE, we need to somehow find n linearly independent solutions. If we do that, we'll have a basis for the solution space. In that case, our general solution will be of the form c1 y1 plus ... up to cn yn, where the yi's formed our basis. Here's that same big idea on the next slide. So I said we need to somehow find n solutions. Let's recall how to actually do that. We'll start with first order ODEs. How to solve something simple like this, y prime plus a of t, y equals 0. First, try to solve it by inspection. Sometimes you can do that. Sometimes it's really simple, especially when a is a constant. If not, then you can always separate variables. Let's do some examples. This first one, solve y prime minus ky equals 0. This one I hope you can do by inspection. If not, I'll give you a refresher. So if you write this as y prime equals ky, you see that a solution is any function y of t such that when you take its derivative, you get the same thing back except a constant k pulls out. So with a little bit of thought, you realize that exponential functions satisfy this, so e to the kt is such a solution. So this is a basis for the one-dimensional solution space. So the general solution is just c times e to the kt. So there's our general solution. For the second example, you might be able to do this by inspection, but probably not. Or even if you can, it takes some hard thought, so it's better to just separate variables. So I'm going to write this as y prime equals ty. And remember how to do this. So you write dy dt equals t times y. And by separating variables, that means we put all the t's on one side and all the y's on the other. So I'm going to write this as dy over y equals t dt. And I'm going to integrate both sides. And over here we get the natural log of y, absolute value y, equals 1/2 t squared plus c. And now let's exponentiate both sides. So I'll put an e here and I'll put an e here. And what we get on the left-hand side is this is just the absolute value of y. And the right-hand side, well, let's see, this is e to the c times e to the 1/2 t squared. Now, this constant e to the c is anything. So e to the c is any positive constant, except we have this absolute value of y, which means that if we take y, we have to put plus or minus in this. So the the moral is you can always just assume that this constant is positive or negative. So instead of absolute value of y, I'm just going to write y equals, I'll call that constant, I'll re-Christian it as c e to the 1/2 t squared. So this is the general solution. It's, as you can see, a one-dimensional subspace. So here, a basis of the solution space was e to the kt. And down here, a basis for this solution space was e to the 1/2 t squared. Now, in an ordinary differential equation, intro to differential equation class, I would go a lot slower with this example than I did here. I would explain carefully why I pulled this c out here and why I got rid of this absolute value sign. But since this is a refresher, it's not the focus of this class, my purpose is just to remind you how to do it. And if you want to look at the details, please consult my old class on differential equations, and I have a whole lecture on solving these first order equations. It's worth remarking that unlike higher order ODEs, for first order equations, this method of separating variables always works. Well, that is assuming we can actually evaluate the integral of a. So let me do an example of the general case up here. So if we have dy dt equals negative a of t dt, and we want to solve this, we separate variables. We get dy over y equals negative a of t dt, and we integrate both sides, and so we get the natural log of the absolute value of y, and we get the negative integral of a of t dt. So we exponentiate both sides, and we get plus, let's put a plus c there, slightly abused notation. So we get y of t equals c e to the negative integral of a of t dt. Sometimes this is written as c e to the negative capital A of t. So this is y of t. So this always works. The only barrier is sometimes you can't necessarily integrate this function, so you just have to leave it as an explicit antiderivative. Let's conclude this lecture with a more difficult case, how to solve second-order homogeneous ODEs. Now, the general case, when a of t and b of t are arbitrary functions, solving an equation like this can be harder and impossible. So sometimes we can use a power series method, or sometimes we can guess and check. But one special case that we learned first, and it arises a lot in things like simple harmonic motion, is when these are constants. So a of t is a constant b, and b of t is a constant q. So for constant coefficients, we always guess that e to the rt is a solution. And it makes sense why this would work, because you take derivatives and you plug this back in each term we get some constant times e to the rt. So if we pick the right constant, we should get these to cancel out. We'll do several examples in increasing order of difficulty. And once again, I'm going to go through these faster than I normally would if I were just introducing this topic in an Intro to ODEs course, because I'm assuming that you've seen these before, and this is just a quick refresher. So the first example, y double prime plus 3y prime plus 2y equals 0. So as before, we always guess that y of t equals e to the rt. In this case, y prime equals r e to the rt, and y double prime equals r squared e to the rt. So we plug this back in, and we get r squared e to the rt plus 3r e to the rt plus 2 e to the rt equals 0. Well, first I'm going to factor out an e to the rt times r squared plus 3r plus 2 equals 0. So we can divide by that, because that's never 0. So this is r plus 1 times r plus 2. So we get r equals negative 1 or negative 2. So in this case, before we say the general solution, we have one solution of the form e to the negative t. That's this root. And the other solution we have is e to the negative 2t. Now recall, the general solution to this linear homogeneous ODE is a dimension 2 subspace. So all we need to find are two solutions that are linearly independent, which means when n equals 2 that they're not scalar multiples of each other. So these will do. So the general solution is y of t equals c1 e to the negative t plus c2 e to the negative 2t. That wasn't that bad, was it? Hopefully this is easier than you remember it from your Intro to ODEs course. Here's our second example. Solve y double prime minus 4y prime plus 20y equals 0. So as before, I'm going to assume that y of t equals e to the rt. So now y prime equals r e to the rt, and y double prime equals r squared e to the rt. We plug these back into here, term by term. Y double prime equals r squared e to the rt minus 4 y prime is r e to the rt plus 20y is 20 e to the rt. We factor out an e to the rt and we get r squared times or minus 4r plus 20 equals 0. Now some of you, if you've done a few of these, will skip right to this step, and that's fine. So let's cancel that. And now, see, that doesn't factor, I don't think. So we have to use the quadratic formula. So r equals minus b, that's 4 plus or minus the square root of b squared, that's 16 minus 4 times a, which is 1 times c, which is 20, which is 80, all over 2a. So that's 2. So this thing here, that's the square root of negative 64, that's equal to 8i. So this is 4 over 2, 2 plus or minus 4i. So this is 2 plus or minus 4i. So what that means is, well, we have two solutions. Y1 of t equals e to the 2 plus 4i times t, and y2 of t equals e to the 2 minus 4i times t. So this means that we have the general solution. We know the solution is the two-dimensional vector space, and these are two functions that are not scalar multiples of each other. So the general solution is y of t equals c1 e to the 2 plus 4i times t plus c2 e to the 2 minus 4i times t. Now if you're remembering your ODEs class, you may be scratching your head thinking, well, this isn't how we solved these. We did something a little bit different. And that is correct. So let me summarize that, what you probably remember from your Intro ODEs course. So far, we know that the general solution to this ODE is a two-dimensional vector space. And we found two solutions. y1 is e to the 2 plus 4it, and y2 is e to the 2 minus 4it. These are linearly independent, and therefore they are a basis for the solution space, because we know any basis has size 2. This is two-dimensional. However, we can find a better basis because we don't really like working with complex exponentials. It's hard to graph these, it's hard to visualize them. So we'd rather use real-valued functions. So here's a cute little trick. So I'm going to write y1 as, I'm going to use the laws of exponents, e to the 2t times e to the 4it, and y2 is e to the 2t e to the negative 4it. Now, do you remember Euler's formula? This is a good one. You should remember this. E to the I theta for any angle theta is cosine of theta plus I sine of theta. Super useful and also pretty incredible. So let's apply that to each of these complex exponentials. One other quick thing. another useful fact is that cosine of negative theta equals cosine of theta, and sine of negative theta equals negative sine of theta. So this first one here, I'm going to write this as e to the 2t times, now theta is 4t. So cosine of 4t plus I sine of 4t. And the second one is e to the 2t. And now theta is negative 4t. So cosine of negative 4t, well, the negative sign just gets absorbed because of this relation. And in this second term, the negative sign pulls out and becomes negative right here. So this is cosine 4t minus I sine of 4t. Okay, so this is y1 and y2. Now what do you want to do? Well, let's add these things up. Let's take y1 plus y2, and look what happens. If we do that, the signs cancel, and we get 2 e to the 2t times cosine 4t. So, well, let's just do this. Let's take 1/2 of y1 plus y2. And now we get e to the 2t times cosine of 4t. So this is a solution. Why is it a solution? Because we expressed it as a linear combination of our basis element. And vector spaces are closed under linear combinations. So this is a solution. Now what else could we do instead of adding these things up? We could have subtracted them. Well, if we subtract these two, then the cosines cancel, and we are left with 2I sine of 4t times e to the 2t. So let me write that out. 1 over 2, let's divide by I as well, times y1 minus y2. This is e to the 2t sine of 4t. So this is a solution. So now we have these two functions, which are clearly not scalar multiples of each other, so they are independent, and these are a different basis. So instead of using these complex exponentials, which we don't really like very much, we would rather use sines and cosines. So to summarize this part, we started with a basis y1 and y2, and we said, hey, look at this. 1/2 y1 plus 1/2 y2 is this function, and 1 over 2i y1 minus 1 over 2i y2 is this function. These are linearly independent, and therefore they are a basis as well. Therefore, the general solution can be expressed several different ways, either as the span of this basis of complex exponentials, or the span of this e to the 2t times cosine and times sine. We usually prefer the latter because we can graph these functions easily, and if we do that, we can write an arbitrary solution as c1 e to the 2t cosine of 4t plus c2 e to the 2t sine of 4t. And now we can factor out an e to the 2t if we want to, and write this as e to the 2t times c1 cosine of 4t plus c2 sine of 4t. And once again, this as a set of functions, if we're looking at all c1 and c2 that are complex numbers, here we have to use complex numbers because we've been having i's in these functions, that is the same as a set, so that's the same as c1 e to the 2 plus 4i times t plus c2 e to the 2 minus 4i times t, if we're looking at all c1 and c2 in the complex numbers. So these as sets are completely the same even though they look a lot different. All we're doing is we're just using a different basis for the solution space. At last, we come to our third, final, and most complicated example. As before, I'm going to go through this at a fairly brisk pace because I'm assuming that you've seen it before. If not, please review my videos from my Intro to ODEs course, where I do this much slower because those are all prerequisites for this course. Okay, so in here we want to solve y double prime plus 4y prime plus 4y equals 0. As before, we assume the solution is of the form y of t equals e to the rt, and then y prime is r e to the rt, and y double prime is r squared e to the rt, and now we plug these guys back into here. And if we do that, well, I'll skip a few steps because we know how this turns out. We get e to the rt times r squared plus 4r plus 4 equals 0. So I've literally just put these coefficients 1, 4, and 4 right here, here, and here. Now this factors as r plus 2 quantity squared equals 0. And that means that we have, well, r equals -2, so we have found a solution, namely y1 of t is e to the minus 2t. This is a solution. Well, unfortunately, this is a second order ODE, so the general solution is a two-dimensional vector space. So any basis has two solutions, has two vectors in it, not one. And we've only found one. And this is the only one of this form, because any solution of the form e to the rt must have r be -2. So we have to find another solution somehow. How are we going to do that? Well, we're going to guess that there's a solution. This is probably how you were taught. It's how most courses do it. Assume that there's a solution of a slightly more general form, v of t times e to the minus 2t. Now we know that a constant will work for v, so we just have to verify that maybe a more general function will work as well, like maybe a linear function. Spoiler alert, a linear function will work. So let's take derivatives. The derivative of this is v prime e to the minus 2t minus 2v e to the minus 2t. And the second derivative, now this should remind you this is done by the product rule. It's a product of two functions. So now we have to do the product rule again on each of these two terms. So the product rule on the first term is v double prime e to the minus 2t times, well, not times, minus 2v prime e to the minus 2t. And then the second one, it's minus 2 times, put some brackets here. This brackets is the derivative of this guy, v e to the minus 2t. Well, that's what this is up here. That's y. So all we need is the derivative of y, which is y prime. So I'm going to copy and paste this whole creature right in here. So I get v prime e to the minus 2t minus 2v e to the minus 2t. Now let's simplify this last thing. So we have v double prime e to the minus 2t. That's a double prime. Now what else do we have? We have minus 4 v prime e to the minus 2t. And we have plus 4v e to the minus 2t. Okay, now what? We have y prime, and y double prime. Let's plug these guys into our original ODE. Okay, so y double prime plus 4y prime plus 4y. So this goes right there. So in other words, this thing goes right there. So this is equal to v double prime e, I'm not good at my double primes, e double prime e to the minus 2t minus 4 v prime e to the minus 2t plus 4 v e to the minus 2t. Okay, my next term is plus 4y prime, so plus 4 times this guy. So 4 times v prime e to the minus 2t minus 2v e to the minus 2t. And finally, plus 4 plus 4y, or 4y is 4 of these guys, plus 4v e to the minus 2t. And this whole thing equals 0. So what we can do is we can factor out an e to the 2t. So we can write this as e to the 2 minus 2t times, well, what's this mess? So how many v primes are there? That's easy. There's one, v double prime, just this guy. How many v primes are there? We have negative 4 here and positive 4 there. So 0 v prime. And then how many v's do we have? We have 4 here, negative 8 right here, and positive 4 here. So that's 0v equals 0. And look at this, it cancels. Spoiler, this should always happen. If it doesn't cancel, you've done something wrong, and check your work. So we can divide through by that, and we get that v double prime equals 0. What does that tell us? So v was this mystery function that we wanted to solve, and now we've said that whatever function this is, its second derivative is 0. In other words, v of t equals some, how do I want to say it, a plus b t. Any a and any b will work. So that means that this y of t is a plus bt times e to the minus 2t for any choice in a and b. Well, we only need one function, right? So let's pick a and b to be as simple as we can. Well, not too simple. If a and b are 0, it doesn't tell us anything useful. And in fact, if b is 0, then we're left with a times e to the minus 2t, which is the same thing as y1. So let's let a be equal to 0 and b be equal to 1. If we do that, we get a solution of the form y2 of t equals t e to the minus 2t. And here we go. Now we have two solutions, and hence we have a basis. So the general solution is of the form y of t is c1 e to the minus 2t plus c2 d2t e to the minus 2t. There is our general solution, and so a basis consists of y1 and y2, which are given as e to the negative 2t and t e to the negative 2t. Now we could have picked something else different for, well, both y1 and y2, because any function of this form, a plus bt times e to the minus 2t, would have worked. So we could have been all cute and picked a and t to be like 2 and 13 if we wanted to, but why would we do that? Anyways, this method is complicated enough, and it really always yields the same thing, is that our second solution is just a t in front of your first solution. So many classes, they just teach that. They say memorize this. Just if you get one solution, then stick a t in front. So maybe in your class you didn't see this method. Or maybe you saw a more general method. There actually is a general method. Now you say, well, maybe the second solution doesn't actually have this form. Maybe there isn't a v of t in general, for maybe more complicated equations. And for non-constant coefficient equations, maybe that's the case. Fortunately, there is an actual algorithmic method that will always work that involves the Wronskian, and we'll learn about that in the next class. Now, some of you saw this in your Intro to ODEs course. I did not teach that. There's just so much material to cover, and I left that one out. Well, my reasoning was because the Wronskian involves the determinant of a matrix, and you need to understand linear independence to understand really what it means, or to understand the significance of it. And we didn't do that in Intro to ODEs. We didn't do that till now. So instead of just giving you a cookbook formula to memorize, and it's also very trivial for first and second order equations,
So really, what's the point? I'm saving it until now that you've seen some linear algebra and you can understand the full meaning of the math behind it. So that is coming up next. Stay with us.